with a quick review from the previous lecture, where we introduced Möbius transformations. Right? We did it via linear algebra, and then we deduced an explicit formula, and so some standard examples, right? So like some easy examples that luckily, that we are so lucky that with those easy examples, we are going to be able to reduce the study of arbitrary Möbius transformations to the study we made of those easy examples. That's kind of a nice coincidence. So the definition was via linear algebra, as I said, and what I did was I considered an arbitrary bijective complex linear map from C2 to C2. Complex linear map from C2 to C2. Bijective, right? Which means that in particular the image of any one-dimensional vector subspace here, its image under such bijective linear map is also a one-dimensional subspace of C2, right? So any bijective linear map induces a function, actually a homeomorphism from P1 to P1, right? So from the complex projective line to itself. And this we called mu sub f, and we said it's the Möbius transformation associated to f. And then we said a Möbius transformation of P1c is any function from P1c to P1c arising in this way, arising as kind of the P1 shadow, the projective shadow of a bijective C linear map of C2. Right? So I would say is a very conceptual definition, right? So it's kind of just the P1 shadow of linear algebra. So a Möbius transformation is just the P1 shadow of a linear map. But then and the fact that this is a conceptual definition allows us to show very easily that Möbius transformations have this composition property, that they open composition, and I would say this is very easy to check. One checks very easily that the Möbius transformation associated to the identity is precisely, is the identity of P1c, right? And then these two things imply that the Möbius transformations of P1c form a group, right? A subgroup of the group of homeomorphisms, of self-homeomorphisms of P1. And that taking Möbius transformation of a bijective linear map is a group homomorphism from the group of bijective linear maps from C2 to C2 to the group of self-homeomorphisms of P1c. Okay, so that's kind of something nice about having a conceptual definition, which is one can prove this in a rather straightforward way. But of course, to work with examples, one needs an explicit formula. So to find an explicit formula for any given Möbius transformation, what we did was we remembered that in the first lecture we gave bijections between the complex projective line and the extended complex plane, and we saw that whenever we have an ordered basis of C2, somehow every one-dimensional vector subspace of C2 can be written in normal form with respect to this basis, right? Where one has this Z V1 plus V2 appearing, or 1 V1. Right? And then if one fixes a basis of C2, let's say the standard basis, for instance, and then one takes a bijective linear map, takes a matrix of this bijective linear map, then one can compute the explicit formula by simply both in the domain and codomain, which are P1C, passing to C bar. Right? And then this way is precisely how the famous formula of Möbius appears. Right? This mu of z equal to alpha z plus beta divided by gamma z plus delta. And this is the formula. So it is passing to C bar. So somehow passing to normal forms that allows us to perform explicit computations. And then we asked ourselves, okay, so let's try and give some easy examples, right? And we saw two basic types of easy examples. One of them were the translations, right? So z goes to z plus beta, right? Which is the Möbius transformation associated to the matrix 1 beta 0 1. And then multiplication by a non-zero complex number alpha, right, which is z goes to alpha z, and it is the Möbius transformation associated to this matrix. Right? For the translations, okay, no, I will come back to the translations. This multiplication by a non-zero complex number, we saw that it has three essentially different subtypes, right? Depending on where my number alpha is located. So, in which of these subsets of this partition of the non-zero complex numbers it is, right? So the identity Möbius transformation multiplying by any alpha in the unit circle is a rotation. Multiplying by any alpha in the positive real axis is just a homotopy. And then we saw the rest, right? This kind of loxodromies. Okay. In any case, for all the examples that we studied, we found two families of curves. One of them consisting of curves, each of which is stable under the action of all the integral powers of my Möbius transformation. Right? In the case of a translation, we saw that I'm referring to these curves. Each of these curves is invariant, stable under all integral powers of translation by beta. And then we saw a second family where these curves have the kind of the transversal property, and it is that the image of one such curve is another curve in the family. And we found these two types of families of curves in all the examples. Right. So let me just briefly go to how they look like in the multiplication by some non-zero complex number alpha. So for positive real number, these curves, each of these curves is stable under multiplication by alpha. Right? So the kind of the rays the rays spanned by non-zero vectors, and the other family, the one that is permuted, is this one, the family of circles. In the case of rotations, well, each circle centered at the origin is stable under rotation, and now it's these rays, or if you want, these lines through the origin that get rotated. the kind of that the image of one member is another member of the family. And finally, in the case of loxodromies, we saw this kind of spirals. Yeah, and then each of these spirals, defined by this formula, is stable on their all integral powers of multiplying by alpha. And then we saw that for instance, the circle centered at the origin, the image of one such is always another such. Okay, and then in all examples, each of the two families encountered found have the property of foliating foliating C bar if we remove fixed points. The fixed points were, in the case of translations, only the point at infinity, and in the case of multiplication by a non-zero complex alpha, or complex number alpha, it was the fixed points were 0 and infinity. Okay, so that's what we did last lecture.